In this video, I'm going to discuss the concept of static equilibrium, when the forces and torques on an object are balanced. And I will walk through several common types of physics problems related to torque and static equilibrium. We're going to start out fairly simple with just a 7-kilogram board placed exactly in the middle on a pivot point where it's nice and balanced. So we can clearly see that the board is not moving and it's not spinning. So the question is, well, why doesn't it move and why doesn't it spin? Well, we know objects, when they're at rest, the sum of the forces is zero. So all the forces are balanced in both the x and y direction. So let's just first think about what are the forces on this 7-kilogram board. Well, it's got a mass of 7 kilograms, so therefore gravity pulls down with a total of 70 newtons of force. But when we're talking about also rotation, we have to not just draw a dot for the object, not just a simple free body diagram or a force diagram. We have to actually draw the entire object and label where the forces are acting on that object. And that gravitational force, where is it pulling on the board? Well, every little bit of mass of the board is being pulled by the Earth's mass. So technically that 70 newtons of force is spread out evenly over this entire board from both ends, and equally to the middle. If the board's getting pulled down with 70 newtons and it's not moving vertically or accelerating in the y direction, we know that the pivot point, its support, has to be pushing up with a normal force equal to 70 newtons. So why isn't it moving? Well, the forces are balanced. 70 newtons is pulling down, 70 newtons is pushing up. Well, why is it not spinning? Well, things spin or rotate when they feel torques. Are any of these forces exerting torques? Remember, torque is defined as the force applied to an object times the radial distance it's applied from the pivot point. So let's just take the normal force. The normal force is pushing up with 70 newtons, but where's the pivot point? Well, let's just imagine the pivot point is over our base of support. There's no radial distance that the normal force has. So we'd multiply the zero distance, it's applied at the pivot point, times the 70 newtons. The normal force exerts no torque. What about the gravitational force? Well, remember, we're imagining the gravitational force as a lot of tiny little gravitational forces. So technically, any one of these little forces that's not at the pivot point, it's at some distance away, some radial distance away, each of those things would be providing some torque. And all these little forces on the right side would try to make the board rotate in the clockwise direction, and all the tiny little forces on the left side try to exert torques, which make the board rotate in the counterclockwise direction. But if we think about it, each one of these forces kind of has a counterpart. The little forces on the end are exerting torques, but they're the same size force at the same distance, so those torques would cancel each other out. And the same thing would be true with every other force. It has its own counterpart. So even though there's a lot of torques on the board, all of those torques cancel out. Well, there's actually a little bit simpler way to think about the gravitational force that's evenly spread over the entire length of the board. We could imagine that all of those tiny little gravitational forces, which add up to 70 newtons, is just acting at one location on the board. It's not, but we can imagine it is, and the physics and the way that we think about problem solving will work out. So we'll test this out in a little bit as well. So we can imagine that the gravitational force on the board's mass, that all of those 70 Newton forces added together, is acting at one location, which is at the center of mass of the board. Which, if you have a board that's the mass is evenly distributed, the center of mass will be exactly in the center. So if we just imagine the one force of 70 newtons acting at the center of mass location, well, now it's acting at the pivot point location, and we say the gravitational force exerts no torque on the board. So let's see what happens when we move the center of mass to the right of the pivot point. You can see that now the force of gravity, as we're imagining acting at that location, is causing a rotation in the clockwise direction. So I'm going to add another mass on the other side to try to exert a torque on the board in the other direction to try to make it rotate counterclockwise. That perfectly balances out, and so we can see the board again at rest, where it's not moving and it's not spinning. So at that location, the torques must be balanced. The board stopped rotating when this added ball was 0.62 meters away from the pivot point, and the center of mass of the board was about 0.3 meters away from the pivot point. So let's find out quantitatively. We know the mass of the board, we know the mass of the ball, and these distances. Are the torques quantitatively balanced? So here's all the values for the masses of the scenario we just saw. The ball had a mass of about 3.3 kilograms, which means gravity is pulling down with 33 newtons. The board's mass was 7 kilograms, so it's being pulled down with 70 newtons of force. And if this board is at rest, it's not accelerating in the y direction, all the vertical forces must be balanced. So if we have 33 newtons and 70 newtons pulling down, that means we must have a normal force of 103 newtons pushing up. The gravitational force was 0.3 meters away from the pivot point, and that 33 newtons of gravitational force was about 0.62 meters away from the pivot point. When we have a situation where all of the forces are balanced, both in the y direction and the x direction, where the sum of the forces in the y is 0 and the sum of the forces in the x direction is 0, we'd say that the object is in translational equilibrium. All the forces are balanced in both different directions. If the torques are balanced, in this case when the board's not rotating, we're going to find out, are the torques actually balanced? We say that the board is in rotational equilibrium. So the torques exerted by any exerted forces would be 0. So we're going to find out, are the sum of the torques 0? Is it 0 Newton meters? This board that's not moving and not spinning, we would say is in static equilibrium. Why? Well, in physics, we define static equilibrium as an object that's in both translational equilibrium and rotational equilibrium. Translational equilibrium just means the forces in any direction are balanced. So if we add up the forces in the y direction, they add to 0, and if we add up any forces or components of forces in the x direction, they must also sum to 0. Well, static equilibrium also implies that the object is in rotational equilibrium, meaning that the sum of all of the torques caused by any forces on the object would all also add to 0. So we're going to find out, is this board in rotational equilibrium? Does the sum of the torques on the system, is it about 0, based on the measurements that we took? So we know it's in translational equilibrium, all the forces are balanced. That's how we thought through the size of the normal force, which is 103 newtons. So now let's take each of these three forces and calculate the torque that they exert on the system. Okay, so we're going to find out the torque exerted on the system or the board by that 3.3 kilogram mass, the torque exerted by the force of gravity acting at the center of mass location, and the torque exerted by the normal force on the board. Remember, when we're thinking about torques, you have to draw the entire object and then label where those forces are exerted and figure out what those distances actually are. So let's start with the torque exerted by that 3.3 kilogram mass. Well, it's the radial distance, remember that's 0.62 meters, times the size of the force. So it's going to be 0.62 meters times 33 newtons, and we can just multiply these two things together because they're perpendicular, the radial distance and the force, so it's r times f, as long as they're perpendicular, and we get 20.5 Newton meters. And this force is trying to make the board rotate in the counterclockwise direction. There's only two spinning directions. It's either counterclockwise or clockwise. And just by convention, these are the signs for the rotation directions. If an object is going to be rotating in the counterclockwise direction, we call that a positive rotational direction. So in this case, this would be a positive torque. And if there's a force trying to make an object rotate in the clockwise direction, we call that the negative rotational direction. We'd say it's exerting a negative torque. So because this 33 newtons is trying to make the board rotate about the pivot point in the counterclockwise direction, we call that a positive torque. So the 3.3 kilogram mass is exerting a positive 20.5 Newton meter torque on the board. Well, what about the 70 Newton force? Well, it's its radial distance times the size of the force. So it's 0.3 meters times 70 newtons. So that's 21 Newton meters. And this gravitational force is trying to make the board rotate in the clockwise direction. And the clockwise direction is the negative rotational direction. So we'd say that it's exerting a negative torque, a negative 21 Newton meter torque on the board. And then the normal force, it's got a large force, but it exerts 0 torque. Why? Because it's no distance away from the pivot point. That force is acting at the pivot point location. So even though it's the biggest force on the board, if we imagine the pivot point right at the support location, that force is exerting no torque. So if we add up these torques, you can see that within a half of a Newton meter, essentially the sum of the torques on the system is 0. So this board is in static equilibrium, and it's because the forces in any direction are balanced and the torques on the board are also balanced. Well, it turns out that it makes sense that if we pick the pivot point here where the board could rotate, all the torques are balanced. What if we change things up a little bit? What if we imagine instead of the pivot point being right here, what if we imagine it being all the way on the right side of the board? And technically this is something we can do, because if a board is not rotating or an object is not rotating, it's not rotating about any point that we pick. It's not rotating about the left side, it's not rotating about somewhere in the middle, and it's not rotating about the right side. So the forces don't change. They're acting at the same location with the same size force. So let's find out, if we imagine the pivot point is over here and recalculate the torques, would we still get the sum of the torques on the system, or the net torque, to be about 0? Let's find out. Well, what does change though? If we imagine the pivot point at the right side of the board, the forces don't change, but the distances those forces are from the pivot point, those do change. So let's figure out those distances. So the gravitational force now, if we imagine the pivot point on the right, it's now half the length of the board over, right? If this board is 2.4 meters, now the gravitational force is acting at a distance of 1.2 meters from our new imagined pivot point. And now we've got the normal force. That's going to be half the board's length plus another 30 centimeters, or 0.3 meters. So now the gravitational force is 1.5 meters away from the pivot point. And this 33 Newton force, it's almost the entire length of the board away. It's going to be the 1.5 meters plus another 0.62 meters. So its radial distance, if we're imagining the pivot point is on the right side, is now 2.12 meters. So now let's go through and calculate the torques. For the 33 Newton force, it is 2.12 meters away, and it's a 33 Newton force. And from the pivot point on the right-hand side, this gravitational force of 33 newtons and this gravitational force of 70 newtons are trying to make the board rotate in the counterclockwise direction, which is a positive torque. The normal force now is going to try to make it rotate in the clockwise direction, and that's going to be a negative torque. So the 3 kilogram mass, or the 3.3 kilogram mass, exerts a positive 70 Newton meter torque, if we imagine the pivot point is on the right side. The force of gravity acting at the center of mass location, that's 70 newtons, it's 1.2 meters away, it's a 70 Newton force, it's exerting a torque of positive 84 Newton meters. And now the normal force, it's not at a 0 distance from the pivot point, because we're imagining the pivot point is all the way on the right-hand side. And so it's at a distance of 1.5 meters away. It's got a force exerted that's 103 newtons, and it's trying to make it rotate in the clockwise direction, which is our negative rotational direction. So we'd say that the normal force is exerting a negative 154.5 Newton meter torque on the system. When we add all three of these torques up, we find the sum of the torques on the system, or the net torque. Again, it's within about a half of a Newton meter. So even if we imagine the pivot point on the extreme side, doesn't matter where it is, as long as you calculate the distances properly and know the forces correctly, any way you do it, the sum of the torques will be 0. Which means when you come to a problem where something is in static equilibrium, you can decide where the pivot point is to hopefully make your life a little bit easier. And we'll do that over some of the next couple problems. So now let's think through a situation where we have to think through torques and static equilibrium symbolically. So the question is, where can you place the base of support so a board of length L and mass M stays balanced when a bowling ball of the same mass, so mass big M, is placed on the left end of the board? So let's say we've got our 7 kilogram board, length 2.4 meters. So we're just going to leave it symbolically. We take a bowling ball that's the same mass as the board, and we put it on the left-hand side. And the question is, where could we put this base of support so that this board would stay in static equilibrium? It wouldn't move up or down, left or right, and it also wouldn't rotate. So let's think this through. Well, we know on this board, there's 2 significant forces. There's the gravitational force acting on the board's mass, right? Which is at the center of mass location of the board. And how big is that force? Well, the gravitational force on anything is just the mass of that thing times the gravitational field strength, lowercase g. And we're imagining it's acting right in the middle of the board. So we've got a force equal to mg acting at the middle here. And if this bowling ball has the same mass as the board, it's also feeling a gravitational force equal to m times g. So we have two forces that are the same size that are trying to make this rotate, but we're trying to figure out where can we put that pivot point, essentially provide a normal force or a location of pivot where everything would stay balanced. Let's go to the extreme. If we put the pivot point at the right side of the board, now we have two forces that are trying to make this board rotate in the counterclockwise direction. That clearly won't work. Or if we put the pivot point in the middle, this force would exert zero torque, but then this one would. So we're going to have to put the pivot point somewhere in between there so that the torques caused by each are balanced. And they're the same size force. And if we want them to exert the same torque, that means they have to be the same distance away from the pivot point. So if we just put the pivot point in the middle of these two forces, that means each of those forces, that's equal to mg, will be at a distance of a quarter of the length of the board. You know, if we calculate the torque, it's R times F. They'd have the same expression for the size of the torque, and they're both trying to make the board rotate in different rotational directions. It should stay in static equilibrium. So let's find out if that's actually the case. So I'm going to take the 7 kilogram bowling ball as close as I can get to the left-hand side and then slide the board over until I can find a spot where it doesn't rotate. It's in static equilibrium and rotational equilibrium. And that should be exactly in the midpoint between the bowling ball and the center of mass location as marked on the board. So that seems to be right about the spot. And if we look at the measurements, within a centimeter or so, from the middle of the pivot point to the center of mass location was about 60 centimeters. And again, from the middle of the pivot point to the center of mass location where the gravitational force is acting is also about 60 centimeters, which is a quarter length of the board. So it works out. The last example I'm going to talk about is a fairly common one for AP Physics 1 when we're thinking through static equilibrium problems. There's a horizontal beam or board attached to a wall, usually on the left-hand side, and then a rope attached to either the end of the beam or the middle of the beam or somewhere in between. And you're thinking through either how much force does the wall exert on the beam or how much tension is in the string, etc. First, I want to show you that what's supporting the board on the left end requires both a horizontal force and a vertical force. You can see here that I'm pushing up with the hand below the board, and I'm pushing to the right with the hand on the side of the board. So the first thing I want to show is if you take either one of those forces away, the board will not stay in static equilibrium. So if we look on the left-hand side here, I'm removing my hand from pushing to the right. And so what happens when I move my hand away? Well, the beam moves left when the horizontal supporting force is removed. So clearly the horizontal supporting force was required. On the right-hand side of the screen, you can see I take my hand quickly away from the bottom of the board, removing the vertical force. And you can see the left end of the beam moves down when the vertical supporting force is removed. You can also, it also starts to rotate in the counterclockwise direction. But both of these videos combined show that whatever's supporting the board on the left-hand side must be both pushing in the vertical direction and the horizontal direction simultaneously. So let's walk through two symbolic problems related to this kind of situation. Here's our horizontal beam that's in static equilibrium. There's a rope attached to the very right side of the beam, and the beam is attached to the wall. This attachment point doesn't necessarily push or pull in any one direction. It actually depends on what else is going on with the beam, where the rope is attached, or if there's anything else hanging off of that beam. So the way that you should think about it is that this attachment point could push up or down. It could exert a force in the vertical direction if it needs to, and it can exert a force in the horizontal direction if it needs to keep this beam in static equilibrium. So the first thing we're going to do is develop an expression for the vertical component of the force, Fy, the wall exerts on the beam, and we're going to express our answer in terms of the board's length, the board's mass, and the angle that the string makes with the board attached at the right side, and any physical constants as appropriate. So the first thing we're going to do is figure out all of the forces and relative size of the forces that the board feels that's in static equilibrium. Well, the board has mass, big M, so it's feeling a gravitational force acting in the middle of the board at the center of mass location equal to big M times G, the gravitational field strength. And strings pull with tension forces, so there's a tension force up and to the left acting at the right side of the board. And we don't know if there's a force in the X direction or a force in the Y direction. So let's think through, does there need to be a vertical force in the Y direction? And if so, how big is it? Well, remember, we can, even though like it might make sense to put the pivot point all the way at the left-hand side where it's attached to the wall, we can put the pivot point anywhere we want to figure out the physics problem that we're trying to solve. And notice, when we find an expression for the size of the y component of the force the wall exerts on the beam, we can't use T for tension. We can use the length of the board, the mass of the board, and the angle if it's appropriate. So if we can't use T, we might want to figure out an equation that doesn't include T. So if we're thinking about adding up torques, like where could we put the pivot point so the tension exerts 0 torque? Well, we could put it at the right side of the beam. If it's at the right side of the beam, it doesn't matter how big that tension force or what the angle is. From this vantage point, it's exerting no torque. So the only thing exerting torques would be the gravitational force of the beam itself, and, well, in this case, it would have to be a vertical component pushing up that the wall exerts on the board. Why? Well, if we imagine the pivot point on the right-hand side, the gravitational force on the mass of the board itself is trying to make the board rotate in the counterclockwise direction, right? And so if it's not rotating, it needs something to try to exert a torque in the other rotational direction. It needs to try to make it rotate in the clockwise direction. And the only other force that could do that would be the y component of the force that the wall exerts on the board. You know, what about the x component? That's at some distance. It's not a 0 torque because it's at a 0 distance. But if the wall is pushing on the beam, this force would be parallel with the radial direction. And if the exerted force is parallel with the radial direction from the pivot point, it also exerts 0 torque. So the only thing that could counteract the torque caused by the weight of the board would be the y component of force the wall exerts on the board. So it would have to be up. So let's figure out how big that would be. So the torque caused by that y component of the force that's in the negative rotational direction because it's trying to make it rotate clockwise has to be equal to the size of the torque exerted by the center of mass, which is the positive rotational direction. So remember, torque is just R times F as long as the force is perpendicular to the radial distance. And for the gravitational force, like R is to the left, the force is down, that's perpendicular. And also for the y component, R is to the left, and the force is straight up, so it is perpendicular. So it's just R times F. So the distance that the vertical component is from our pivot point is the entire length of the board. That's R right there. And the size of the force is F sub y. How far away is the gravitational force from the pivot point? Well, it's half the length of the board. So it's R 1/2 L times F, which is just equal to m times g. So now let's just solve for the vertical component of the force. Notice there's an L in both sides of the equation, so if you divide each side of the equation by L gets canceled out, and it turns out that the y component of the force, or an expression that's equal to it, is just equal to half of the weight of the board and has to be pushing up. Let's just see if that makes sense. Would a y component that's half as big as the weight exert the same torque as the full weight? Well, it would actually, because that force is twice as far away from the pivot point as the larger force. And remember, with torques, as R is doubled for the same size force, the torque is doubled. So each Newton all the way at the left end is twice as effective at causing rotation, is as effective as every Newton that's exerted in the middle of the beam. Now that we know the wall is at least pushing up with a force in the y direction equal to half of the weight of the board, we can find an expression for the size of the tension in the string. Well, this board is in static equilibrium. So the question is, develop an expression for the tension T in the rope attached to the beam of mass m and length L. And again, we're going to express our answer only in terms of the board's length, the board's mass, and the angle the string makes with the horizontal, and any physical constants like the gravitational field strength of the Earth. So we can, again, imagine the pivot point anywhere we want to. We don't want to put it at the right-hand side because we're trying to find an expression for T. So if we're adding up the torques or getting a sum of torques equation, we want a T in it so we can get T equals something. We can put the pivot point wherever we want to, but it makes sense to either put it in the middle of the board or imagine it at the very end of the board. Either place you put it will actually end up getting the same expression, but let's just put it in the middle of the board because I think it's probably the easiest. If we imagine the pivot point in the middle of the board, now the gravitational force acting in the middle exerts 0 torque. But there's a torque exerted by the y component of the force and now a torque exerted by the tension. Let's first split up tension into its y and x components. Tension is up and to the left, so it's got a vertical component and a horizontal component. And the only thing that matters is this perpendicular piece of the force, or the tension in the y direction. The amount of tension in the x direction exerts no torque, just like the amount of force that the wall exerts on the board exerts no torque. So we basically have the torque exerted by the y component of tension balancing out rotationally the torque exerted by the y component of the force that the wall exerts on the board. If the pivot point is in the middle and those are the two things that have to balance each other torque-wise, they're at the same distance. They're both half the board's length away from the pivot point. So if the y component of the force on the wall is equal to half the weight of the board, that means the y component of tension also has to be equal to the same size, 1/2 m times g. Well, we want to figure out an expression not just for the y component of tension, but the actual tension. So that involves the angle that it makes with the horizontal. So here we have our little right triangle. The tension that we're trying to find an expression for is the hypotenuse of this right triangle, and we know how big the opposite side is of that right triangle. So if theta is between the horizontal direction and the tension, that means this angle is also theta. These are alternate interior angles. So let's set up a simple algebraic expression to solve for tension. The y component of any right triangle is equal to the hypotenuse times the sine of theta, because that's the opposite side of our right triangle. So the y component of tension is equal to t sine theta, and we figured out that the y component needs to be equal to 1/2 m times g, half the weight of the board, because it's the same size as the y component of the force the wall exerts on the board. So Ty equals the actual tension times sine theta. So all we need to do is divide each side by the sine of theta. And so we get T, or the tension, is equivalent to the weight of the board, m times g, divided by 2 times the sine of theta. I hope this video has been helpful in helping you think through what it means for an object to be in static equilibrium. Remember, something where the forces are balanced and all the torques are balanced, and several different example problems to help you think through how do we apply that and using the concept of torque to solve common AP physics problems.